Hello, everyone. My name is Hugo Dorado. I'm a Biodiversity Sea Alliance researcher. Today's presentation is a prescriptive analysis and optimization. This is part of the foundation of information analysis and data mining in agriculture that's being developed between the Biodiversity Sea Alliance, Illinois University CIMMYT, and the CCAPS project. This topic talks about one of those steps of the data analysis to generate results that allows to take specific decisions. In the data analysis projects, four different types of analysis can be being identified that can be represented in a sequence of difficulty. And one step is harder than the other one. The first one is a descriptive analysis, where we evaluate what happened with the data, where we just do an exploration without having so much information, previous information that can be found there. Once the results are obtained, we carry out a diagnosis where we try and understand that relationship better. Also, the trends that we found based on our descriptive analysis. There are some hidden signs in that step, but once we go to the predictive analysis, we have more signals that are clear. We try to build a model that allows us to estimate what could happen afterwards based on certain characteristics. The last step and the last classification for analysis would be prescriptive analysis. And that's where we respond the answer of what are the actions that we have to take so that certain situation that's convenient for our problem could happen, could materialize. So this is the point where we do the optimization based on that prognosis. And to do that, we have to go through the previous steps before. From the prescriptive analysis, we aim to find the optimal solution when we have a series of possibilities where we are trying to take a better decision based on an objective that we have outlined. It differs from the predictive analysis because we mainly focus on which decisions can be taken and what actions can be taken and what recommendations can be generated. In the predictive analysis, we are mostly focused on being able to develop a model that allows us to estimate the information that's going to happen in the future. In this case, if we already have that model, the idea is to identify how we can have a scenario with a better future for us. And the advantage of prescriptive analysis is that it allows us to offer specific information in order to take a decision. In the prescriptive analysis, this is very linked to the concept of optimization. And this concept looks for a distribution that we want to assess and decide what's the maximum point or what's the minimum point. It depends on the function that we are evaluating. For example, let's say that we are working on yield and profitability. We're probably talking in those cases to maximize. But if we talk about costs or amount of diseases that appear in our crop, then we would try to minimize. So the optimization basically tries to identify what's the solution that will allow us. Well, it's a process that allows us to guide ourselves to reach that optimal result based on the objective. If we take this problem to agriculture, a predictive model, we could talk about the different factors that affect the yield, the sustainability. We already saw this before, like the climate, agronomical management, and the soil are the main factors that affect this variable. So this could be a mathematical model until this point. And we could think that the variables that are involved in weather, the ones that are involved in soil and management, are the ones that will help me to predict that yield. So far, I haven't spoken about taking any action, but at the moment when I declare that my objective is to increase the yield, increase the sustainability, then I go from my predictive model to an optimization strategy. Because what I want to do at that moment is to identify what are my best scenarios so that my yield can be the best and to take a decision based on that. In order to work on an optimization problem and our yield issue, we could define an F function that could be a function that we can train with machine learning. And this is known in this context of optimization as an attitude function. And this allows me to transform this set of variables that I can use to have an estimate of my solution or a response value or attitude value that we're going to see, aptitude value. And these possible variables are the set of variables that can take any value. So seen from this standpoint, this will be my aptitude value. So we know that as I define that I want to implement this aptitude, then I'll look for the values that allow me to reach that objective that I've outlined. Some examples, let's say that we have, if these two variables represent precipitation, humidity, depth, amount of nitrogen, monitoring, etc., this could have values like the ones that you're seeing on the screen. So there could be many different solutions if I work from this standpoint. If I would like to look for the conditions that will help me to achieve a better yield, then the model could test infinite possible solutions if we assess the decimal numbers that we could have here in these values. And the idea of the optimization is trying to identify what's the maximum among different solutions. So that's the main purpose in order to be able to take decisions. Now, the optimization problems can be solved in two different ways. The first one would be with exact methods that will guarantee to find the solution, the optimal solution of the system that we are assessing. So the search for that optimal solution can tell us that we have to previously define a mathematical structure of the objective function that we are evaluating. And this could complicate things when we are using a function based on machine learning, where most of the methods used there are black box methods. It's not so easy to approach them mathematically. Therefore, it's not going to be easy to find a solution, a mathematical solution based on formal methods. This could also be assessed with a simulation by trying all possible solutions and combinations of variables that we have available, but computationally speaking, that could become impossible. The more variables that we have, and if those variables have many possible values, it's going to be harder. So, as an alternative to those exact methods, we have approximate methods that use iterative algorithms, and the solutions of the system are approximations. The disadvantage is, of course, that they do not find the global optimum. Instead of that, what they do is to look what we know as local optimums, which are close solutions to the global solution. So it does not guarantee finding that solution, that optimal solution, but an approximate solution. But the advantage is that the solution can be found faster, which can also be important in what we want to develop. Because many times we need to give an answer basically in real time. So we could not solve that with exact methods. We would need too much time to do that. And another advantage is that it's not necessary to define a mathematical function. These methods usually explore the solutions that are candidates to have a better potential. And to do so, the algorithm works with different approaches, and one of them is known as meta heuristics. Meta-heuristics are abstractions of real events that are turned into algorithms which want to solve an optimization problem. Among them, we have genetic algorithms, which try and find solutions based on certain operations like crosses, mutations, and replacements to find the solutions that have the most potential. Another method that's very well known is the optimization of particulate matrices that use the behavior of animals that work in hives to look for food, and, and they interact among each other. Another meta heuristic that's well known would be the ant walk, that just like with the hives, it used certain signals to trace the search of their food, and each one of the individuals play a specific role. And finally, we have the search for harmony, the harmony search, that is based on the search of musical compositions where the musician uses his knowledge and improvises different harmonies to build a song. So the objective of the different algorithms is to deal with this search. They begin with an initial solution that has been outlined based on a predictive model, a simulation. They start to explore the different possible solutions, all possible solutions that are generated from that search. So the idea is that not everything's going to be searched. Otherwise would be an exact method. We'll just explore the meta heuristics, and this will trace the most probable road to find a local optimum. And if we're lucky enough, we have the possibility to that meta heuristics could find a global optimum. But this will help us anyway to find a decision to put in place in the future. Now, going to our agricultural problem where we planted predictive modeling and we have the objective of carrying out an optimization. In this case, we could identify among our different set of variables candidates, and there are some non-controllable factors by the producer, like the weather and the soil. These are variables that the producer cannot manage, and even climatic aspects have to be considered based on a weather forecast or a climate forecast, because we don't exactly know what are the conditions that are going to come in the next season. But there are factors that are controllable, and these are the agronomical management factors. And this is where the potential lies, where a decision can be taken based on what he wants to do with his crop. And this has to be based on these characteristics that are non-controllable. These non-controllable characteristics could vary from a producer to another producer, but they are going to be fixed. The controllable variables can change as far as the producer is willing to do it, and they produce a better condition in what we are assessing. In this case would be yield. If this is approached mathematically, we're going to have a formula like the one that we saw before, where each one of these groups of variables is going to be defined based on the position here. And the function that we would use would be that for each one of the producers, we are going to have this part of fixed variable. While every grower has the potential to um, apply different agricultural management options until they find the best one that's going to be based on these variables that are going to be fixed. And the objective is to maximize if we're talking about the yield of and sustainability. Once the values are fine-tuned to find the best practices for management, we could offer specific information to each one of the producers. Since the optimal that can be used by certain growers that have different conditions would be the optimal for another producer that has different conditions here, and that would be fixed in order to find that optimal value based on an optimization strategy. This is an example of a case study that we made in Chiapas. one of the most recent cases that we've done jointly with the CMIT, where we built a predictive model very similar to the one that we had before that we shared with you. And we have climatic information for soil and agronomical management that we used for this random forest that had enough predictive value of approximately 73% in that function of predicting the yield. So what we did with that function is to try and identify a similar process to each one of the producers. The producer begins with a management that will give them a yield of 5 tons per hectare. But we can use that predictive model to begin and solve or search for different solutions to see what happens if he changes his agronomical management. And based on a climate forecast, we could start to identify what are the practices that have the most potential. And to do this search, we use this global best harmony search. What did we like about this algorithm? Why didn't we use genetic algorithms or Hive optimization or AntWalk? It's because this algorithm gives us enough flexibility to combine quantitative and qualitative variables inside this model for optimization. So this gave us a flexible possibility since we had those conditions in our database. For each one of the producers, we were willing to do the same process. And this algorithm would help us to identify in that search process what was the best possible condition for management practices that could be applied by the producer in order to reach those optimal results. So we found processes like this one where he had certain current practices, like the one that you can see here, where he did two applications of herbicides, one of insecticide. He used 117 kilograms of nitrogen per hectare. He did not use phosphorus or potassium. He, he used a cultivation practice that wasn't very popular in the region. And he did not do seed treatment, but he used cultivation with preservation. After carrying out this optimization, we were able to identify practices where he could produce um, increase the production in 2 tons per hectare, and we could identify that the practice that had the most potential would be P4082, where he should try treat the seeds. He should focus on preservation. He should apply insecticide applications from. He should increase from 1 to 3 insecticide applications. So based on this process that we were proposing, what we did was to apply this on the whole database of producers that we had. So what you can see here in red would be the current distribution with the current practices that they have in place right now, the producers have in place. As you can see, the average would be 3.67 tons per hectare and a lot of variability. It's estimated that's of approximately 5.44 hectares per tons per hectare. The challenge that we wanted to propose based on this data analysis process that could generate these specific recommendations based on optimization and prescriptive analysis is to displace this distribution to one that's more focused on the right side of the plot so that every producer can exploit their resources the best they can to increase that yield average in 1.77 tons per hectare. As we can see here, the distribution in blue, that's when the producers applied all the practices that are optimized. The additional advantage of using these techniques is that we also have the capacity to reduce the variability from 5.44 to 0.55. And this would be our proposal for contributing to closing the productive gap. So based on this solution, the producer can be given specific information per site so that they can take better decisions. Key points of this presentation, we're able to define that concept of prescriptive analysis, and we know that what allows this analysis is to find optimal solutions for improving the decision-making process. We identified also that one of the ways to implement that prescriptive analysis would be the computational optimization, and among these we have the meta-heuristics. Meta-heuristics have the advantage that it yields solutions faster compared to other methods like exhaustive methods, and it can give solutions that are close to the global optimum. And we were also able to identify that the yield analysis based on climatic variables, soil management, and management variables can be um, approached with optimization where meteoristics are used. And this process is able to generate information on agronomic and management per site so that the producers can take better decisions. So with this, we end this presentation. I hope that you liked it. And I'm going to wait for the next presentation for questions.